Great, thank you. So thank you all for having me today. This has been a great day. It's excited to see so many people engaged in this. My name's Sean Dague. I'm a software engineer in the IBM Q group, which is our quantum computing effort, which is a joint effort between IBM Research and systems within IBM. Today I'm going to talk a bit about quantum computing in general, IBM stuff in specific, especially a bunch of our open source stuff related to that and how you can jump in. My goals for all of you is to, this is a big, complicated new area of research that's like on the leading edge. We are learning a lot as we go. So what I want to give you is a flavor of what's going on, why a new type of computing is interesting for certain problems. And then actually like answer the question like, oh, I want to learn more. How would I go and do that? And we'll go through that. And we'll show some live stuff as we go. This is actually all done inside Jupyter Notebook, so we'll be executing code a little later on. So one of the first sort of questions is like, why might we need to dive into a new way of thinking about computing? And there's reasons for that, right? While like we deal with the world at a macro scale and like this looks like it's a big hard thing made of steel, at the end of the day, this is mostly empty space. That the way it's really interacting at a microscopic level is all about quantum physics. And that's true of like everything that we're here and exist. And a lot of modern technology uses these facts to actually solve their set of problems. But in order for us to simulate like the real world at these small scales, we build these really complicated models and do a bunch of approximations. And we put those all in a supercomputer and we get useful but not exact results. So the world is not actually a classical world, it's a quantum world. And we can use some of those features if we can actually compute with base qubits to get some better answers and to get answers to problems that we can't get answers to otherwise. How many people have taken a physics class and are familiar with the double slit experiment? All right, I'll do a quick refresher for everyone else as well, because this becomes important when we start thinking about why how quantum mechanics works a little bit differently and why we might be able to use some of this stuff in an interesting way. So the double slit experiment, as we were starting to learn about how light really worked 100 years ago, one of the things that was done, if you take two sufficiently small slits in a piece of material and they're close enough together and you shoot a coherent beam of light, like a laser, through them, what you'll find is that on the backside you don't see two slits. What you see is this pattern where it's sort of brighter and darker and brighter and darker and brighter and darker. And what's the reason you get that is because turns out light is a wave, and so much like waves in a pond, these will interfere with each other as they come through these slits, and they create constructive interference, which is bright areas, and they create destructive interference, where the waves come and they're exactly mismatched phase, and they basically cancel each other out, and you create these dark areas. What was one of the extremely surprising things we learned about nature is that while this is true of light, which it kind of had senses that light was a wave for quite a while, when you do the same thing with a beam of electrons, you get the same pattern, which meant that electrons, this fundamental particle that everything, all atoms have a bunch of, acts like a wave or has wave-like properties. It does a thing that we know waves do, which is constructively and destructively interfere. That was quite surprising. And that's one of the reasons why when you hear people talk about quantum mechanics, they'll talk about like wave-particle duality. What that really means is, the electrons aren't exactly a wave, they're not exactly a particle, there's something else that, depending on how we look at them, we see the properties that we know we see in waves. And this is a good example of that. So let's start diving into some base things about the fundamental building blocks of quantum computing. And the first of which is a qubit. All right, so how many people feel like they have a good handle on what a bit is? Right, so how would you describe a bit? A 0 and 1, great. How many people know what a bit looks like in hardware? Sure.
I remember core processing.
Well, a physical ring, yes. Yeah.
That's the best physical description I can remember.
Yep. So in a modern computer, we don't actually have physical rings we're flipping anymore, which is good because this phone would be really big. But at like the lowest level, what a bit really looks like is a line voltage, right? Typically, you've got depending on the computer, you'll have a 3.3 volt logic system or a 5 volt logic system. And what that really means is that somewhere along the way, we just define an arbitrary cutoff. It's like on a 5 volt system, like more than 4 volts, that's a 1. Less than 4 volts, that's a 0. Right? But it's actually on the wires, these things aren't exactly 5 volts or 0 volts at times, right? Depending on how the whole mechanism works. But we throw away all that intermediary information because for the abstraction and the computing that we need, like it's actually not very useful. There's a whole alternative field that of analog computing where like that intermediary stuff is interesting. For quantum computing, we have this concept of a qubit. And a qubit, you can think of this as called a block sphere. What it is that the state of a qubit is some point on this sphere in like 3-dimensional space, which really is defined by a couple of different phase angles. At the end of the day, we can only measure on one axis here. So we will measure this to the 0 or to the 1, but its real state is not a 0 or 1, and it's not even a 0 or 1 at the same time. It is somewhere along this sphere, and we can manipulate that along that sphere. And doing so, before we take a measurement, we get access to the usefulness of it being in one of these intermediary states, and we use that as part of the processing. And we'll show analogs to how that is, and then some experiments later. One thing that I want to make abundantly clear is that no one that's moderately serious about this space believes that quantum computing replaces all of classical computing. That's just like not really a thing. What it is that there's a world where there's easy problems, and you can do easy problems in lots of ways, right? And then there's sufficiently interesting and hard problems that, in a classical sense, we build enormous supercomputers to solve some of these problems. But there is actually classes of problems where you just can't physically get enough space or memory, or the fact that the approximations that we have to make in classical computing, they break down. So this is general accepted belief that what we've got is a class of problems which will be easier to do on a quantum computer, and then some that you just will like literally never be able to do on a classical system. And part of that is that we can use for things like computational chemistry, we can use the actual quantum properties of the qubits to mirror the actual quantum properties of electrons in complex molecules. And so that you get results that look much more, you can use those quantum properties to make sure that you've got results that actually match what would happen in a quantum system. At the end of the day, there's some constructs here that will become important in the abstract, and we're going to go through a bunch of these pretty quick. Don't worry if you don't grab every one of them, it's fine. We'll show some hands-on later. The first of which is superposition. That was the thing I was talking about before. A qubit is not in a 0 state or a 1 state almost all of the time. It is in some other intermediary state. And we generally, this is referred to as a superposition. You may be able to construct this linear algebra-wise, you can construct this as a set of vectors. Like, what is the portion on this vector position and this? And you have different axes, so you can also describe it as a set of matrices. There's the concept of measurement, which is, it's great that this is in some intermediary state, that quantum state, and we can use that fact, but we can't actually see that. When we take a measurement, this collapses to either the 0 or 1, and it does so probabilistically. So if you were in this state, what you would actually find is that, like 75% of the time, this would collapse to a 0, and like 25% of the time, it would collapse to a 1. And so taking one measurement doesn't give you very much information, because this is a statistical distribution. So when we do quantum experiments, what we actually have to do is run this sufficiently large numbers of times, the same calculation, to get the statistical model of what's going on with the system. So very common on our quantum systems, you'll typically run 1,000 shots. So you'll set it up, the environment, and it will run the experiment, the same experiment, 1,000 times, and give you the probability distribution of, this is what we measured out of those 1,000 times. And you'll see, like, oh, it's more probably this than that. The last of which is entanglement. And this is where there is kind of no analog to classical computing. You can have certain qubits, you can entangle them with others, and such that operating on one impacts operating on the other. This is actually, this is an actual quantum chip. This is a 5-qubit chip that IBM's produced. These are where the qubits hang out. These bits in between are the resonators that let you couple these qubits together. Today, with the actual quantum systems that exist, you typically can't entangle any qubit to any qubit. And so this becomes an interesting part of building software that you can then actually compile for exactly the chip you're going to put this on, because its physical layout matters if you want to try to to get entanglement happening in certain ways. Yeah, we'll jump there. When we talk about quantum computing in the state of maturity that's in right now, we are talking about this in terms of gates. So this is very low-level operations, right? Like if you think of it in a classical sense, we did a digital logic class or something, and you were looking at AND gates and NOT gates and NOR gates, and how would you build logic out of this to get you the right answer? We're back to that. That's where we're at. We're building a gate system for qubits about how they will manipulate with each other and how you will get answers and how you will measure on those. But we have a whole different set of gates because these qubits act differently. So this H gate, which we'll see later, this is the Hadamard. This puts a qubit into superposition. And then these are C0 gates, and so these entangle these two qubits. So a value here will impact a value there, and then we measure things. And every time we measure things, we collapse the quantum properties of the system, and it's it is now actually a 0 or 1, and then we move forward. So in this case, we put something in superposition, we measured it, and that meant it was no longer in superposition. We had to redo this again if we wanted to have quantum properties of that qubit. So we talked about the double slit experiment up front, and this is where it becomes interesting in terms of how it impacts computing problems, which is we know that quantum systems act like waves, and now we've created these things called qubits, which are some logical construct, and we can talk about what the physical representation actually is. But they have all the same wave quantum properties. So if we set up our problems correctly, we can use those same wave interference properties to do things where we have made the wrong answer to a problem become less probable to show up in the distribution curve, or the right answers to become more probable. And when you hear about things like the coming concern around cryptography and quantum computing and how it would impact that, what this comes down to is there was an algorithm called Shor's algorithm that was written, which said when we have fault-tolerant quantum systems, which we don't have yet, and they have thousands of qubits, which we don't have yet, then we can use that property to build up factoring problems where we can use this fact to basically zero out a whole bunch of the wrong answers to a factoring problem. So you can massively reduce the search space. And there are generic algorithms for reducing the search space on text as well that uses the same properties. So as anyone who's studied like cryptography and security is like, if you have a 4,000-bit key, but you could actually reduce it to like a 500-bit key problem, like you've gone from intractable to I can go crunch that in a supercomputer. And so that's the concern. It won't just like immediately spit out like all the encryption is broken, but for encryption that depended on factoring being a hard problem, you'll get some abilities to reduce that search space using these methods, and then it becomes a lot simpler. So we're not there yet, but it's good to know when you draw a curve of like, we're going to get there, to start working on the problem early. So there's a whole research field right now working on quantum safe algorithms that do not depend on factoring being hard to keep their secrets. And the fact that we're working on that now means that we will be ready by the time this comes knocking on the door. All right, that was a bunch of theory, there's a bunch of concepts. If like every single one of those didn't like land and internalize, don't worry, that's fine. But this is a flavor of kind of why this is interesting and why we're headed there. So let's actually do some real quantum computing now. We'll show some examples. To do this, I'm going to use Qiskit, is the open source software that IBM has created for doing quantum computing. You can download it, qiskit.org. It's available on, it's all written in Python. You interact with it with Python. And it includes all these components. So it includes Terra, the base, like compiler and everything along with it. Air is a high-performance quantum simulator you can run locally. And then there's some other tools when you're doing more advanced things. Aqua is trying to build up, not everyone wants to program everything in gates, right? Like how many people here want to like program everything in gates? Like no, right? So Aqua is an attempt to take some of these well-understood quantum algorithms and do a higher level implementation of them that translates down to like what gate structures would you set up to actually solve that problem. So I'm just going to start running this. We're going to do some stuff in the simulator locally first. You just kind of import your tools, away you go. I'm going to do the simplest possible quantum circuit in the world, which is I'm going to take a measurement. This is not like exceptionally interesting. There's one qubit. By default, qubits initialize to the 0 state, and then we're going to take a measurement. So we can do the really exciting, let's look at what this looks like. For single qubit results, we can actually, in the simulator, we can do a thing where we can kind of see what those states would be. So this is where we start off. This is the qubit we created. And if we measure it, I'm going to do it this way so it'll come back on the screen. What we get is there is a 100% chance that it will be in the 0 state because that's what we did, right? This is the simplest quantum circuit in the world, and it's completely uninteresting. But it gets us started, right? We're going to build layers. So the next thing we can do is realize that these things have gates, right? We talked about there being gates, but we don't have like the not and and nor gates that you're used to. They have different gates relative to this. And what gates in a quantum space, this is an X gate. What this actually means is that we're doing a rotation So an X gate is doing 180-degree rotation around the X-axis. So now that 0 qubit will be a 1 qubit all the time. And if we see that, we have now 100% chance that's in the 1 state. Great. OK. This is slightly more interesting quantum circuit, but not really all that interesting yet. This is the first time we're going to do a quantum thing. And in order for the state vector simulator to work correctly, I'm not actually going to apply a measurement because that would destroy the intermediary. But this is the H gate, the Hadamard gate. And what it does is it puts the qubit in superposition. So that means we're going to do a 90-degree rotation around Y. So when we measure this, what's it going to look like? Does anyone have a guess? Yes. Except, it's also a statistical probability, which means if you actually do a measurement and we have to do it 100 times so that we have like a certain amount of results to skew, we got them 53 times over here and 47 over there, right? Our CHASM simulator tries to actually inject the similar amount of noise that you'd see on a real set of hardware, so that won't be a 50-50 perfect answer. Yes? This is all in Python. This is all Qiskit code and running in a Jupyter notebook right now. Yep. OK, cool. So yeah, we'll just get past that. There's other gates that exist, right? We can like rotate around other axes. That's cool. We can do these like funky things where we rotate, like we've rotated down this way and then we rotate around that way. That doesn't impact the measurement per se, but it would impact how this might couple with other qubits. Things become slightly more useful when we start actually looking at, let me make sure I've got this. OK, so right, 1 qubit, not very interesting because you can't really solve that many problems with 1 qubit, like no problems. But we can have more than 1 qubit. So in this case, we're going to have 3 of them. And now it becomes a little more interesting to kind of interpret the results graphically, because what you really end up with is what is the chance that each thing is in 0 or 1 state. So we can do that. And then the other thing is that if you were really thinking about this in terms of like all the spheres, you also have to think about what was the chance of that in every axis direction. So this is like the real plane and this is the imaginary plane. And we didn't do anything to these things, right? They're just like, I guess we did. This is going to be a 0 and these are going to be 1s because it's an X gate. So as you'd expect, it's like 100% chance that it's like 1, 1, 0. Entanglement, right? Here's where things get actually interesting in a quantum sense, where 1 qubit's now entangled with the other, which means that whatever the state is on the first one, it will also drive on the second one. So a C0 gate means if this is a 1, then this will be, then apply a naught, an X naught. So this will then also be a 1, because this would have initialized as 0. So given that we did this, where we put this qubit into superposition, and then we did a C0, does anyone have a guess on what this graph is going to look like? It's going to be what? 100% 1, 1. That's one guess. Anyone else? All right. So this can be in 4 states. Sorry, it can be in 2 possible states. It can be in the 1, 1 state or the 0, 0 state, because this gave us kind of a 50% chance of being in either. But if this is a 1, then this will be a 1. If this is 0, this will be a 0. And if we measured the first one, we'd find we know the answer to the second one without having to measure it. So with that said, right, this is a simulator. You can do all of that like on your laptop, install Python, install Jupyter, away you go, play with the simulators. There's a ton of tutorials, and I'll point you to some more specifically. But what's, people have been writing quantum simulation stuff for like 50 years. Maybe not as slick as this, but like that's not a new area. What's new is the fact that we have real quantum devices now. This is a quantum computer. This is actually the quantum chip, and it sits at the bottom of this thing, which looks like all these crazy gold wires. We call it the chandelier. This is actually just a refrigerator. Because the way a quantum system actually looks is that you have this canister, and I heard some folks made it up to the Poughkeepsie site and got to see the tour. So when you looked at this big canister, what you're looking at was a refrigerator. At the bottom of that refrigerator was the actual quantum chip. The rest of it is just a whole way to get to 15 millikelvins by using liquid nitrogen and 2 forms of liquid helium. And then next to it is a bank of microwave transmitters. Because that's how these things are actually programmed. They have resonance frequencies in the microwave range, and that's how you send data down to them, set them up in certain states, entangle them, as well as read out the data. And then attached to the microwave transmitters is like a classical computer that's driving all these things to generate the waveforms to do all of this stuff. Some of you know this already, but basically, so IBM's got quantum systems we make available to the public. They're all within 75 miles of here. Some are at the Watson Research Center, and some are at the IBM Poughkeepsie site. That's where more of our new production systems are going in. And as of this date, we announced it on this date. I think it went live like 30 days later, was the 53 qubit machine, which is biggest in the world. And that's sitting up in Poughkeepsie. All right. So let's actually run something that's a real quantum algorithm on a real quantum device, which we can do right here. And we'll do this with more Qiskit. So in this case, the difference is I am actually attaching to my quantum experience account. And I'll show you how you can do that afterwards. We have, oh, come on. Oh, I clicked in the wrong region. Okay, so there are a whole bunch of quantum computers. I have access to more quantum computers than you'll see during the quantum experience. But there's a whole bunch of them because we make some systems available to the public, like a whole bunch of 5-qubit systems. These are the topologies associated with them, as well as a 14-qubit system, IBM Melbourne. And then we have this thing called the IBM Q network, where partners have access to some larger devices. That includes a bunch of 20-qubit devices. This is the 53. There's this 1-qubit device, which will be interesting someday. This is the device we're going to run on. It is called Valencia. And there's a couple other devices publicly available that you can have that will have basically the same properties, which is Orance. I think Orance and Vigo are publicly accessible there. So what you're looking at here is a topology map. And this topology map is which qubits can be entangled to which others. If there's a line between them, we can entangle between those two. So we have to think about this in terms of like logical and non-logical qubits. You can get a whole bunch of information about what the error rates are of these things. So the state we are in computing right now with quantum is that it is not a fault-tolerant system. Like there is some error rate associated with writing the value you want in a qubit with doing any of the quantum operations. Those errors build up over time. So there's a whole set of the software libraries designed to enumerate or to help characterize those errors, make some guesses about them based on the results you're seeing, and sort of do signal analysis afterwards to factor them out. But in a lot of ways, we are at like the computing stage, like the ENIAC time, right? Like where you had like big computers that filled a room. Like our computers don't quite fill a room, but like they're there. You're directly manipulating bits. So this is a quantum algorithm. It's an old one. It was developed like before anyone was really like working on quantum computing systems in a real way. And it's a weird thing, right? So it's this weird, like, hey, so if this algorithm says that if you had some program that would either generate balanced output, which means that like half the answers are 0 and half are 1, or that it always, regardless of the inputs, you always get a constant value. There's a quantum way to know that that was true about a thing in a single operation. So I won't try to explain all the details of this because it's like, it's a little bit of a funny edge case. But realize that the development of quantum algorithms is like a pretty fundamental thing all by itself, and like building quantum algorithms that solve different and interesting problems, like that's a whole field of research. But given that, we're going to build a 4-qubit version of this because we actually need to use one of the qubits to help us get the right answer. So this is what the algorithm actually looks like in Python. This is available in a tutorial on the Qiskit.org site. This is what the gate structure looks like for it. It's a lot of superpositions, this X0, an entanglement, and then a bunch of operations. But this is the logical version of this. If we're going to send it to an actual physical quantum system, we can't necessarily entangle these two qubits to each other. So we need to compile for the system that we have. And depending on how we optimize that, you know what I'm going to do is this is a little bit randomly different each time. Let's see. Yeah. Okay, so this is what in a first pass you'd have to do to couple all these things together to get this to actually run on the topology that we have. And depending on how you optimize it, there are ways to like more highly optimize that answer. We're going to submit it to an actual quantum system. This will take real time because I'm behind someone else in the queue right now. We're also going back to the wonderful days of batch processing because there are more than this number of quantum systems. This is the first time I get to give a talk and say that are available. But it's still small, and they're still sitting in a couple places. So what we do is we make those available via the cloud, via this IBM Quantum Experience. And what I'm going to do is I'm just going to while that's doing its thing, we'll come back to it. And I'll talk a little bit about quantum experience, and then we can do questions, and we'll see how long I have to wait in the queue. So if you go to, I did not helpfully put the URL in here. If you go to quantum-computing.ibm.com, you can sign up for the IBM Quantum Experience. Anyone in the world can do this, and we make, I believe, 5 devices publicly available today for users. 4 of them are 5-qubit devices, and 1 is a 14-qubit device. And the kinds of devices evolve over time. So we are like making better devices available. In this environment, it's got a whole bunch of documentation about like, hey, what do these gates actually do and mean? It's got this thing called the circuit composer, where you can interactively just sort of drag and drop gates onto a thing, and it gives you an immediate simulation of what's happening if you created that circuit, and then you can send it off to an actual quantum system as well. Yeah, what do these gates really mean? A bunch of examples along with them. and a hosted Jupyter Notebook environment. So you can just like, don't need to actually install anything on your computer, show up, generate Jupyter Notebooks, and do work there within the system. And so let's see if our job came back yet. Nope. All right. I will say thank you. Here's a couple of URLs. We will come back to the screen while we talk questions, because I think we have a little more time before we go to our next thing. So, questions from the floor. Yes?
If you wanted to directly exchange values between qubits on two different quantum machines, would you need to go through a digital format to go between with the microwave transmitters, or can you do that in some other quantum entanglement way?
Today, there's no way to do that within kind of the existing systems. This is, becomes an interesting thing to think about. Does the space evolve to the point where we can set up entanglements between multiple systems? And I think that's a big open question that would be very interesting. So yeah, today you'd basically have to kind of pull information out, send it somewhere else, and that path is just is honestly not a useful path in terms of its latency and impacts. Maybe someday. Yes? We have. There's a textbook that exists within the Qiskit community for doing a quantum computing class based on Qiskit and the quantum experience. There's another book coming very shortly to print, Dancing with Qubits by Bob Suter, who's one of our folks. I've seen him holding a physical copy of it, so we are very close to that being out where you can purchase that. But yes, there was another third-party textbook using the same sort of technology that did this too. Yep. Yeah, right off the internet. And there's a whole bunch of tutorials and videos. That's a big part. We have a whole community team that's just working on doing training and videos. Because one of the biggest challenges in this space, right? We are at the forefront. This is, a leading edge bit of computing where we actually don't know all the ways where this might be useful yet. And one of the biggest limiting factors in pushing that frontier forward is the number of people that have the experience with the space to be able to make contributions, right? So 5 years ago, if you wanted to program a quantum system, you had to be a PhD physicist in one of 6 university labs in the world, right? So that's how you got to work on a quantum system. And today, if you want to program a quantum system, you need to have an internet connection, right? Because these systems we've made available for I think 3 years now have had something up there. They've gotten better over time, and a big part of that is the commitment to the community of one of the biggest gating factors of exploring this space is expertise in the space, and so we want as many people as possible to be able to experience it and make a contribution. Yeah. Yep. So the question being, which flavors of math are most relevant? At the end of the day, this is a ton of linear algebra, so that's super critical. Everything really, when you look under the hood, is matrix manipulations, and and you can get the qubits, their expressions as matrix expressions as well, and do it on the linear algebra side. Statistical analysis is also critically important there, and those are the two I would say which are the most important for the space. Yes. How much am I spending? I don't know the answer to that. I'm not. I have a.
How difficult to maintain the temperature?
So those dilution refrigerators, when they go, they stay at that rate kind of continuously. They need to be fed like nitrogen and helium. So the chip stays at its. You get it down to temperature and it stays, right? And it has to be maintained, obviously, with refills of liquid nitrogen and helium. And then, as people's experiments come through, we're basically in between experiments, we're microwave resetting the chip back to a known ground state, and then we move forward on that. Yep. But if there's any other, make sure we got first questions from people first. Yeah.
So most of the chandelier is just pulling it down.
Yeah, and if you think if what those like looped wires are, that's actually the microwave signaling wires coming down and being done in such a way that there's a bunch of errors. We talked about these error rates in the chips, but there's also a bunch of errors just associated with noise in the environment, right? So a lot of that is like there's a whole class of problems about how do you get rid of as much noise as possible in the wiring harnesses that are nearby, because that will impact things. Yeah. Yes. Mm-hmm. Yeah. So a big part of that is one of the open source tools that I didn't talk about is this toolkit called Ignis, which does error mitigation and characterization. And so that's building that kind of tooling and making it available to people so they can understand that. The thing is, even with the errors, there are some tricks to quantum computing itself where you do this thing called a phase kickback, where you basically sacrifice some qubits to garbage to re-enhance signals on ones that you know are going to be good. So there's techniques in programming the systems as well. And as I said, we are at this early explore phase. So a bunch of the clients are working on problems that they think, as we evolve the hardware with them, when we hit certain crossing points, they're going to get a lot of value out of it. But a lot of it's early explore, right? And a lot of the early, there's been a couple hundred papers published using IBM systems from a variety of organizations. And a lot of that looks like chemistry simulation kinds of things, like battery research is something a lot of folks are spending time on. That, we're in a world where we need to come up with some good energy storage solutions. So finding out ways to simulate what's possible. Hey, I got through the queue. Yeah, I was supposed to have priority on the queue too. So what we'll see is that, so there's actually only one right answer to this problem, which is this one. But, we ran this 1,000 times, 1024 times. We did see little bits on these others, and a big part of this is just the errors inherent in the system. Some of them were write errors. The qubit wasn't set in the state that we thought it was when we ran the rest of the algorithm. Others were read errors. But, with a human eye, you can see this was the right answer on a small set of things. And you could imagine you could apply a set of tools, be them statistical, be them machine learning based, that would filter that noise level out for you as well. Yeah, but we mostly waited in the queue. Yeah. Yeah, the bottleneck right now is the fact that there are a small number of actual quantum systems, and so a number of folks using them. And as we see those demands grow, like so at the beginning of the year when I joined the team, I think we had 5 systems online, and now we have 14. So we've been adding capacity as needed. There is a certain rate at which you just can't, these are experimental fields. They're not, you can't just go down to Best Buy and buy a quantum chip, right? Making the chip's kind of hard all by itself. So, right, yes. So, but, there's a commitment that every one of the, as we get sort of new generations of approach, those systems themselves actually have smaller noise levels, like the new 5-qubit systems we added in the fall to the public side, which this is one of them, have much smaller noise rates than the ones that we had out previously. And that, for most people's sets of problems right now, you'll hear in the press people talk about, when are we going to get to 1,000 qubits or whatever. That's actually not the hard problem right now. The hard problem is the noise floor. And so that's been one of the bigger focus areas we've had of like, how do you get the noise floor lower to the point where standard analysis tools will give you the right answers.
Is a shot analogous to like one clock cycle of emitting and reading, or as you were showing like those gates, there are multiple steps?
Yeah, so a shot would be going through this whole thing to the end.
Okay.
So it's all the setup, all the manipulation, right? Every one of these is going to be microwave pulses to do this. These are gate transforms, and then reads. And so one shot is that once.
A complicated one takes just as long in real time as a...
No. So there is real time associated with each of these, and that is one of the challenges is that the other thing besides noise is coherence time, which is you set up quantum systems, and just by the nature of them being quantum systems, over time they decay out to the point where they are indistinguishable from noise. We publish, and it's here somewhere. The qubit properties has it. These T1 and T2 times are coherence times for individual qubits of like how long they will be able to live in some quantum state before they collapse. You can notice those things are in microseconds. Is a small amount of time. So actually, like certain circuits, like if you build a gate depth that's too big, you will like literally run out of time to get an answer before the answer is garbage. So that's part of the hard problems to be solved too, is the compiler problem of like, can we be much more clever? Because what we're actually trying to optimize for is time in the system. And so even if that might mean like more operations, but they happen parallel at the right times, like if you can pull that in within the coherence time, then you can get better answers. So yeah. Cool. Yes?
Okay, I think the computation is very fast. Do you think temperature fluctuation affect your output?
Temperature fluctuations would definitely affect error rates for sure. Yes, and once you, the chip. So I'll end it. This will be. I think I'm at my time. So I'll do this as the last question, and talk a little bit about what are these qubits actually, right? Like, because we just kept talking about them. So there's actually like half a dozen ways to build them. IBM's qubits are superconducting qubits. They use this thing called a Josephson junction, which is like an almost connected transistor wire, but not quite. And in this, at 15 millikelvin, which is we can create a superconducting environment where the physical qubit is actually the fact that current is going both directions at the same time. And so that's actually our qubit. Has to do with current flow and direction. And so that definitely gets impacted by temperature, right, in terms of how well these states work. And this superconducting qubit, that's the same technology a lot of other people are working on. Rigetti, Google, fundamentally works the same way. There's other people that are working on other things, ion traps and whatever. They work differently. They have different fidelity and properties associated with them. Cool. Well, thank you all.